Good morning, everyone. Today I will be presenting our project on Perceptron-based simple texture classification using GLCM features. The goal of this project is to classify two different textures, such as brick and grass, by extracting statistical texture features from image patches and training a perceptron to separate them. This presentation will walk through the problem, the concepts behind GLCM and Perceptron, the mathematical explanation, code implementation, and the results, including scatter plots and classified image patches. This slide explains the core problem we're solving: automatically distinguishing textures like brick and grass. Traditional image processing struggles because visually similar surfaces can still have very different texture patterns, and raw pixel values don't capture that. To handle this, we extract meaningful texture features using the GLCM, which describes how pixel intensities relate to each other. These features give us a statistical signature of each texture. Finally, we use a perceptron, a simple linear classifier, to learn the differences between these features and accurately separate the two texture classes.
This slide introduces the two core concepts of our project, GLCM and the perceptron. GLCM, or the gray-level co-occurrence matrix, is a statistical method that describes texture by examining how often certain pixel value pairs occur next to each other at a specific distance and angle. From this matrix, we extract important texture features such as contrast, energy, homogeneity, and correlation. These features help us quantify how rough, smooth, or uniform a texture is. The perceptron, on the other hand, is a simple binary linear classifier. It learns a decision boundary that separates two classes based on their feature values. Below that, we have the key mathematical concepts. The GLCM itself counts how often pixel pairs appear, and the formulas show how each texture feature is calculated. Finally, the perceptron equation, W1x1 plus W2x2 plus B equals 0, represents the straight line boundary it learns to divide the two texture categories. Together, these concepts form the foundation of our texture classification system. In this code, we build a complete pipeline for texture classification using GLCM features and a perceptron. We start by importing NumPy, Matplotlib, scikit-image, and scikit-learn. Then we add a small compatibility fix to ensure Gray Comatrix and Gray Coprops load correctly across different scikit-image versions. Next, we define a safe gray function. This checks whether an image is already grayscale. If it is, we keep it as it is. If not, we convert it to grayscale. This prevents errors when loading different types of images. We then load the brick and grass images, convert them safely to grayscale, and confirm their shapes. After that, we extract 32 by 32 pixel patches using the extract patches function. These small patches become the samples for training. For each patch, we compute two GLCM-based texture features: contrast, which measures intensity variation, and energy, which measures texture uniformity. These features give us meaningful numerical descriptors of texture. We then combine all feature vectors into X and create labels Y, where brick patches are labeled 0 and grass patches are labeled 1. Next, we train a perceptron using these features. Once trained, the perceptron learns a linear decision boundary described by the equation W bar 1x1 plus W2 x2 plus B equals 0. We extract these weights and use them to draw the decision line on our scatter plot. The scatter plot shows brick and grass points in different areas of the feature space, and the blue dashed line represents the decision boundary learned by the perceptron. Finally, we classify all the patches using the trained model and display a few sample patches with their predicted labels. This visual confirmation shows how well the perceptron distinguishes brick from grass based on their GLCM features. This slide shows the feature space created from the GLCM values, specifically contrast and energy, for both brick and grass patches. Each point represents one patch, red for brick and green for grass. You can see that the two textures naturally form separate clusters. The blue dashed line is the Perceptron's decision boundary, which it learned during training. This line effectively separates the two classes, showing that even simple features can successfully distinguish textures. This slide shows the classification results for individual texture patches. Each small image represents a 32 by 32 patch taken from the brick or grass textures. The predicted label is shown above each patch, where 0 represents brick and 1 represents grass. From the results, we can see that the Perceptron consistently predicts brick patches as Class 0 and grass patches mostly as Class 1, showing that the model has successfully learned the textural differences. This visual comparison confirms that our GLCM features and Perceptron classifier work effectively in distinguishing the two textures. In conclusion, this project shows how GLCM features combined with a simple Perceptron can effectively distinguish between brick and grass textures. It highlights how classical texture analysis and basic machine learning can work together for accurate image classification. In the future, we could expand this by adding more GLCM features or using advanced models like SVMs or CNNs for higher accuracy. These ideas are useful in many real-world areas, from medical imaging to industrial inspection.